Hello, everyone. So this video is about drawing Lewis structures of acids. So first of all, we have to know how to recognize acids. Acids are covalent compounds that they normally start with an H. So the H is usually at the beginning of the formula. And what they can do is they can give away the hydrogen ion, which we call it a proton, towards the process of being an acid. So for instance, we have H₂SO₄, HNO₃, H₂CO₃. So all of these are acids and their H's are highlighted in yellow. However, there are cases that the H is not necessarily at the beginning of the compound. So how do we decide on that? That's going to be the case for the organic acids. So organic acids are the ones that their H normally comes towards the end. It's at the end. So it's the last H. So usually they end with COOH or they are like NH3 plus or something similar to that. So they're like a positive ion of nitrogen, basically. So it's a protonated amino group. So I don't know how much you know about organic chemistry. So organic compounds are the ones that they start with carbon and hydrogen. They usually have carbon and hydrogen in them. And in some cases, they can have also other atoms like oxygen or sulfur or nitrogen attached to them. So in those cases, the H's connected to the C are not acidic. So it's just the H that is connected either to the O or to the N, which is acidic. So in the case of the first one, CH3COOH, the H at the end is acidic, not the rest of the H's. Same thing for the second example. And then same thing goes for the third example. All right, so we're going to take a look at some examples for drawing the Lewis structures of acids. So I'm going to show you all the steps that we have to follow. I had another video before that shows you all the steps for drawing Lewis structures. So this is exactly the same steps for drawing the Lewis structures of the acids, except for there's one additional step at the beginning and a step towards the end. At the end, there's one extra step as well. So I'm not going to go over the steps right now. I'm not going to read them over them. If you want, you can pause the video and take a look at it. However, I'm going to tag my other video over here, which it shows you step by step how to draw the Lewis structures. Okay, so let's take a look at some examples here. So something like H₂CO₃. What we have to do for drawing the Lewis structure of this acid is first we have to take away the proton. So that's what I was showing in the first step in the previous page, on the previous page. So you have to take away the protons from it to figure out what the polyatomic anion is. So after you take the H's out, you're left with CO3 with a charge of 2 minus. Make sure you take H positives out, the protons out. So then when each hydrogen has a charge of +1, so when you take both of them, CO3 will have a charge of 2 minus. Now we just draw the normal structure for CO3 2 minus. So we count all the valence electrons. So carbon is in group 4, so it has 4 valence electrons. Oxygen group 6, so it has 6 times a 3 because we have 3 of them. Plus the overall charge is -2, so we have to add 2 additional electrons to it. So in total, we have 24 electrons. Then we make 3 single bonds attached to the central atom. And then we subtract the 6 electrons that we use in the drawing so far. So we're left with 18 electrons. Then the next step is to satisfy the octet for the outside atoms first. You don't go to the central atom yet. So we have to start putting lone pairs on the outside oxygen. So 3 goes here, 3 goes here, and then 3 goes here. So this way, I'm using all my 18 electrons. So I have no electrons left. Now, this is where we have to do the check step. So step 7 was the check step where you have to check for octet. You have to make sure every atom is satisfied with the octet rule. Of course, there's some exceptions like hydrogen that only needs 2, but most atoms need 8. And then in the cases that your central atom is in the 3rd row of the periodic table or after, then they can have expanded octet, meaning they can have more than 8. So later, you will see you have to use the formal chart for that. So I will tag another video here that explains the octet rule and the exceptions to the octet rule. So if you don't know that, you can watch it over here. So now let's do the check step for every single atom. So we see that oxygen is satisfied with 8 electrons, so it's good. This oxygen is good. This oxygen is good. But when we look at carbon, carbon is not good. It only has 6 electrons. So that means the structure is not finished yet. That's where we have to go to step 8, which is we have to start making double bonds or triple bonds to satisfy the octet for every single atom. The reason is because we have no electrons left right now. We have 0 electrons. So I can't just randomly put some electrons on central carbon. So because of that, what we do is we can take one of the lone pairs of one of the oxygens on the outside away, and we can make a double bond. And if we do that, now if you check for the octet again, you will see that this oxygen has 8, this oxygen has 8, carbon has 8, and the oxygen at the bottom has 8. So therefore, we're good with the octet for all of them. So the structure looks good. Just one thing to make sure every time you draw the Lewis structures is take a look at the central atom. And if it's in the third row and after, you have to check for the formal charge to see if that's a good structure or not. But since carbon is only on the second row of the periodic table, it's happy with just having 8 electrons. It cannot have expanded octet. Therefore, our structure is good. Okay, and now this is the part where you have to attach the hydrogens of the acid to the compound. So what we do is that we have to connect the hydrogens to the single bond O's. So for doing that, we have to connect it to these two O's that they're single bonded. So we take one of the lone pairs of the oxygen out, we attach a hydrogen there, and then we have another hydrogen. So we do the same thing, take another lone pair out from the other oxygen, and we make another single bond H. And this would be the structure of our acid. Okay, so let's take a look at another example, something like HNO₃. So as we said before, we have to take the proton away to find the polyatomic anion. So when we take the H plus away, we have NO3 minus. We do the electron counting. We have 24 electrons. Attach 3 single bonds to the nitrogen in the center. So far we use 6 electrons, so we still have 18 electrons. Then we have to put the electrons on the outside atoms first to satisfy them with the octet. So 2, 4, 6 here, 6 here, and then 6 here. So now we're done with all our electrons. So we don't have any electrons left. So again, that's where we do the check step again, step 7 for octet. So we see this oxygen is good, has 8 electrons already. This one is good. This oxygen is good. But then when we look at nitrogen, nitrogen only has 6 electrons. So it's not satisfied with the octet. That's where we have to go to step 8. So what we do is we take one of the lone pairs of one of the oxygens away, and we start making a double bond between them. And now if we do the check, this is good. This is good. Nitrogen is good. Now it has 8 electrons. And the oxygen at the bottom is good too. So we're good. Again, central atom, I take a look at it. If it's in the third row, I have to watch for formal charge because it can have an expanded octet in some cases. So we see that nitrogen is only in the second row, so it's happy with just having 8 electrons. So the structure is good now. So now it's time to attach the hydrogen of the acid to this compound. So to do that, we take the lone pair of one of the single bond oxygens away, like this one, for example, and we attach the hydrogen. I could do exactly the same thing for the other oxygen on the right, but doesn't matter. It's just the same thing. Just keep in mind that the hydrogen cannot be connected to the double bonded O. It should always be connected to the single bonded O. All right, let's take a look at another example. So this time we have H₂SO₄. So we take the hydrogens away. So we're left with SO4 2 minus. Count the valence electrons. Do the 4 single bonds. So we used 8 electrons so far. We're left with 24. Then we start putting electrons on the outside atoms. So 6 here, 6 here, and then 6 here. So far I use all my electrons. Now it's again time for the check step. This oxygen is good, 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 but sulfur actually is also good. However, this is the part that I said the central atom is belonging to the third row or after, so meaning it can have expanded octet. So this is the time you have to use the formal charge to decide if this is the best structure for this compound or not. So we have to assign the formal charges. So here's the formal charges for every single atom. Again, I'm not showing you how to find a formal charge in this video. I'm assuming by now you know how to find a formal charge. If you don't know, I've made another video that I'm tagging over here where you can learn about finding formal charges. Okay, so we assign the formal charge, and then based on the rule for formal charge, we know that we need to minimize the charge separation. So meaning we don't like to have that much +2s and -2s. We prefer to have more +1s, -1s, and preferably all zeros, basically. But however, since the structure has an overall charge of 2 minus, there's no way I can have every single atom to have a formal charge of 0. So at least 2 things can have a formal charge of -1, and then the rest can be 0. And that can only be achieved by making 2 double bonds. So what we do is we take the lone pair of one of the oxygens away, we make a double bond, we do the same thing from another oxygen, we also make a double bond. So now if you assign the formal charges, you will see that everything is 0, only 2 oxygens are -1. So, and that's perfect for this structure because the overall charge is -2. All right, so this is the best Lewis structure of SO4 2-. Now it's time to attach the hydrogens of the acid. So what we do, as we said before, is we connect them to the single bond O's. So one goes here, and then we do the same thing. One goes to the right one. And this would be the structure of H₂SO₄. Let's take a look at the last example, H₃PO₄. So take the protons away. So we're left with PO4 3-. Count all the valence electrons. So 32 electrons in total. Attach 4 single bonds to central P, -8. So we have 24 electrons left. We start putting lone pairs on the outside oxygens first. So 6 here, 6 here, 6 here, and 6 here. So we're left with no electrons. Now it's time for check. So in terms of octet, all these oxygens are good. And then phosphorus is also good. So this structure so far looks good, but again, because the central atom belongs to the third row and after, it can have expanded octet. So what we have to do is we have to assign the formal charge to decide if this is the best structure or not. So when we assign the formal charges, we have 4 things to be -1, and the phosphorus at the center is +1. So since our overall charge is 3-, that means we have to, the best structure would be something that has 3 things with a -1 and everything else to be 0. So I can only achieve that by making a double bond between P and one of those. So to do that, we can take one of the lone pairs away from the oxygen, one of the oxygens, and then we can make a double bond. And then when we assign the formal charge, as you can see, 3 atoms have a -1, those are the oxygens, and the other oxygen is 0. Phosphorus is also 0, so this is the best Lewis structure for PO4 3-. And now it's time to put the hydrogens for the acid, attach the hydrogens. So as we said, we have to connect them to the single bond O's. So we take this away, make a hydrogen attached here, another one here, then another one here. And that's it. So this is the structure of H₃PO₄. All right. I hope you enjoyed this video. If you enjoyed it, please make sure to like it and follow for watching more videos I'll be posting shortly. Thank you.